VLPSos here. This is a video lesson for Python programming, masking GUI. GUI stands for Graphic User Interface. What we're starting with is the code for proximity GUI. Proximity and masking are different techniques in order to get user input. The user is interacting with an on-screen button, and the pressing on the button from the user's perspective then affects motion on the screen. There's a few different techniques because the style of buttons that we want to make available to the user could change, and we need an accurate way of detecting the appropriate input. We're going to take a look at what we accomplished with proximity GUI first. Then we'll make some changes and switch it to a different technique called masking. When I run my program, I have a green square that I would like to move around. I have on-screen buttons. Those are simple graphics for the user to interface with. In proximity graphic user interface, it's excellent for buttons that are in the shape of circles because the technique is about finding when there's a click, the distance between the hotspot of the mouse and the center of each circular button. If that distance is less than the size of the button or its radius, then we know that the click must have happened inside the button, so we then know to affect the corresponding motion. That is a very efficient technique for a graphic user interface. We're going to switch to masking. But first we need to take a look at the code that accomplishes the proximity, because we're only going to need to change a few parts of it to convert it over to this new style. So our code has two classes, one for the object that we move around and another for a button. We make 4 buttons. The attributes of a button are its name, and its name is being used to also identify what kind of motion comes from that button, a location on the screen, size, color, whether the button is active. There's a Boolean value, it's called attribute active, and if the button is turned on, if this Boolean is true, then we know in our code to check for active buttons and then make the corresponding location change of our object, but only for those buttons that have this Boolean active to be true. This is at the heart of turning our buttons on and off and coding for the corresponding movement. We have added in this code a couple of new attributes, and these attributes are going to be necessary for the masking technique. We have a point list of relative vertices. That's because the new technique is going to be able to take polygon or use or show polygon graphics, buttons that could be very complicated in shape and still interact with those buttons with pixel perfect precision. And we need then also a masking color, which we will talk about when we make the switch to that technique. The find distance function was used to detect the distance between 2 points, mouse cursor and center. This was a necessary function. The math is basically the Pythagorean theorem to find the distance between 2 points. That was necessary for proximity graphic user interface. So we can comment this or this function out because it's not going to be used in the masking technique. We start the function which drives the program. We have a new set of variables that are equal to the point lists. Again, the new buttons are going to be polygons, not circles. And polygons could be of any shape, as we'll see the example of. In order to create a polygon, we need a list of its vertices, which are the points that are then connected by lines in order to make the irregular shape. So here we've defined for our 4 buttons some point lists in order to create those polygon buttons. And we create a dictionary and make our 4 instances of our buttons with these arguments. We've used the point list for each button here. Then we begin our frame loop. There are 4 for a procedure of 4 steps in order to go from the user clicking on the screen to actual motion being seen. A quick review of those 4 steps begins with, at the bottom of our frame loop in the event queue, though there are many keys that are detected to do subtle things in this program, the one thing that affects the motion in the event queue is simply on the event of a mouse button down, and that button being number 1, we have the Boolean variable left click assigned to be true. That's it as far as detecting events from the user. The user simply clicks anywhere on the screen. That left click Boolean is assigned to be true. And then in the frame loop at the top, we go to step number 2. This is the highlights visually where the frame loop begins. So this here is the top of the frame loop. And on left click being true, we go through this code block of immediately signing it to be false, so it only happens once per frame, once per click. And then we iterate through our buttons. There are 4 buttons instances that we made. Now, we're still coding for proximity detection, so we needed to find a distance, and we called the find distance function that we previously saw to see if the distance of the click was close enough to any one of the buttons. The most important thing is this block here may turn one of the button's active attributes to be true. We can think of this button as being turned on. Once a button is turned on, then we go to the 3rd step. We iterate through the buttons, and we check to see if the active attribute is true. We're looking for active buttons. And when we find an active button, we turn its Boolean false. So again, this only happens once, so it has to continue to happen and continue to process if we're going to continue to see the motion. But then it checks its name attribute, what kind of button is active, and assigns the Boolean, the appropriate Boolean for the direction of movement based on whether we found, what button we found to be active. So if the left button was Boolean's active was equal to true, then this assigns it toggles the step left variable to be the opposite of what it was. So this is also a toggle movement. The pressing on a button will turn that corresponding movement on, or if it's already on, it'll turn it off. And it's this code block that then we distinguish or get our 4 direction variables to be either detected on or off. And then once we have that, we go to the 4th and final step, which then checks those Booleans, the step left, step right, up and down, and if they're true, we finally do some math to the position attributes of the object that we're moving. That's the final step. We actually are changing the position so that when that object is drawn, it's drawn in a different position and the user sees that it has moved. Now, switching over to masking is going to just require a couple of different changes. The first change that we're going to make is we're going to make our buttons look differently. We're going to make them look like they're going to be polygons instead of circles. Polygons are much more sophisticated shapes. We've set up for that because when we created our instances, we created them with the attributes that they'll need for this change. All we need to do is, when drawing them at the bottom of the frame loop, which is here under the comment draw objects, we have the square object that we're moving being drawn, and then we're iterating through the buttons and drawing circles. We are going to uncomment code that has been prepared here under the comment draw them as polygons, and then comment out the drawing of circles. Hopefully we can see the change immediately on the screen, and we do. These blue odd shapes are our new buttons, and they are very different than circles. I purposefully made them a little odd in shape in order to highlight how different interacting with these buttons can be. So I haven't affected yet the detection of these buttons. We can't use them in the sense that clicking on them isn't going to work, because the code for detection is still the proximity method, even though our buttons look different. So they're acting like circles, but they look like polygons. The next change that we're going to make is take away the proximity and code for a different detection. The detection that we would need so that when the user clicks, the user ought to be able to see that if they're clicking precisely on the pixels of those odd shapes, then it'll turn that corresponding direction on. We are going to do that with this technique called masking. What masking is this, it's a long and slow process, but it allows us to detect interaction between shapes that are irregular. What it requires is creating another surface, a surface that is the size of the screen. And on that surface, we have versions of the buttons that are drawn in different colors than what the user sees. And the idea is the surface, this extra surface that we're creating, we could call it the mask, has a version of all the things that can be interacted with on the primary screen. The user never sees this surface that we call the masking surface. The user only sees the screen that's presented to them. But when the user interacts with the surface by clicking somewhere, what happens is we check on the masking surface the location that was clicked on. And the masking surface is going to have all the things that can be interacted with represented as shapes that correspond and are congruent to what the user sees, except that all of those shapes are going to have their own unique color. So masking for interactivity with the user, for detecting what the user is interacting with, is the strategy of offering a surface or creating a surface that then when it's clicked on, we can detect the color at that click, and depending on the color of the object, since all the colors are going to be different, we know the one that the user intended to click on. So I'm going to explain this again as we show the code for accomplishing it. First of all, we have to create an additional surface, and it's going to be the same thing as the screen, because there needs to be a correspondence between the things that the user sees and then the masking surface that we're going to check for interaction. So they're the same size. I've created that surface and I've called it masking surface. Now, when I draw buttons on the screen for the user to see, and we've done that at the bottom, near the bottom of our frame loop here, this is drawing the buttons, and it first must use it iterates through the buttons that we have to draw, but this is a little more sophisticated than a single call to the polygon, because we have our buttons drawn on the screen arranged in an ensemble with the 3 buttons on the bottom and the 1 on top for moving up, and they're in the bottom left corner, the bottom right corner of the screen. So what we had to do is we had to create an attribute for the vertices, the points that make up the polygon, but then change each of those vertices based on the button location on the screen. So this code goes through a process of taking the vertices which belong to the button and then doing some simple math so that they become the locations on the screen where that button goes. And we populate the modified vertices in this list, and that's the one that the polygon function uses to actually draw it on the screen. If that explanation is a little confusing, then take it as given that this block of code draws the button to the screen. And we call it 4 times, once for each button. Look at the color that is drawn. It's going to be blue. The user sees all of the buttons as the same color blue when the user looks at the screen. But remember, there's a second surface called the masking surface that corresponds to the screen. And we're going to uncomment this block of code where the very same process is taking place, finding the vertices that we need to create the polygon relative to the ones that are the attribute of the button, and then using the list of vertices to draw a polygon with the polygon function. But the color is now unique. Every button has a different color. The user sees them all as blue, but the color that's drawn on the masking surface is going to be what we call the masking color of the button. And that masking color is different for every button. And when the button got created, when we made our instances, I made sure to assign a different color to each button. So the masking surface has 4 buttons drawn in the very same place as the user sees on the screen, but they're different colors on the masking surface. Now, what colors are they? Let's take a look at where we created our 4 buttons. Here are the 4 buttons that we made, and we can see that the color is blue from the palette, but we have an additional argument called the masking, and every button for the masking attribute was given a different color when it was created. And this is a very long line, so we have a button that has a masking color of orange, purple, yellow, and brown. The attribute that color is the value of is in our init function. We call it the masking color. Now, let's see what the effects that we have just coded for, how they are changing our program. We have the screen. The buttons are these unusual polygon shapes. This is what the user sees, the buttons as blue. We can't fully interact with them yet because we're showing now the difference between the buttons that the user sees and this masking surface. The masking surface is the size of the screen, and I've implemented the space bar like a pause. I can turn on and see the masking surface. Now, when this program, or when you create programs with this technique, when you finally publish them for people to use and to distribute, you wouldn't show the masking surface to the user. The masking surface is a surface that is just used for utility, not to assemble graphics to be shown. But we can see here, for the purposes of our understanding, what the masking surface looks like. I drew some words on it. It says masking surface. And notice that the buttons are the same shape in the same location, but not blue. You're looking at the color that was chosen to be the masking color of the button. That means that from the user's perspective, if I click on any of these buttons, I think I'm interacting with the one that I can see. But what I'm going to do in my code is check when I click, if I clicked anywhere on a button, and find the color at that location in order to be able to tell which button I clicked on. We have yet to implement that part of this. Let's do that now. So previously, for proximity detection, this was the second step in that 4-step process. The first step being there was a left click. And when there was a left click, that second step, which this is the code block for, was to go through the buttons and find the distance between the mouse cursor hotspot and the center of the button. And if that distance was close enough, then we can make the active attribute true. We're going to abandon this by commenting it out and uncomment what was prepared for checking the masking surface in order to see what button we ought to make or turn on or make the active attribute true. So let's see what this code does. Again, if there's been a left click, then we immediately assign that Boolean to be false. So we only are doing this once per click per frame. Then it has a variable that's assigned to the getAt function, what is returned from the getAt function. And the getAt function will get the color tuple at the surface that this function is being used on. It's being used on the masking surface. We're not checking the screen. We don't want to know what blue button was interacted with. We want to know on the corresponding masking surface what color was at that click. And so we're getting at the mouse location where there was a click on the masking surface, and that becomes the masking color check. Now, for the purposes of observing the color tuple that we actually get, we're going to print it. But this line is unnecessary, and we'll turn it off when we have checked that we understand what we're doing. But with that color, what we do is we iterate through all of our buttons, and we check to see if the color we got from the masking surface is equal to the masking color of the button. Remember that each button has its own unique color. So by comparing the color that we got on the click to whatever color our buttons could be, we can find the button that matches. And if we found the button that matches its masking color with the color that we got on the masking surface, then that's the button that we turn on or make the active attribute true. Which then, of course, is all we need to go through step 3 and 4, where we react to what buttons are on and off. So there's no need to change anything after this. Let's see what we got. Now this is what the user sees. This is the screen. Again, this is not something that a typical program would show. Wouldn't show the masking surface, but I can turn it on by pressing the space bar to look at the colors that I'm actually interacting with. Now back to the user's perspective. If I click somewhere definitely not on top of the buttons, then I can see that there was the color tuple that I got from the masking surface is printed here. And that's a color tuple that is for black. It has 0, red, green, and blue. Let's see if I can get idle back here while I run my program. Now I have window confusion. I'm going to do a restart. I have too many windows on my screen. Back to interacting with the program. So I can color detect on the screen and I get black. Now when I click on any one of these blue parts, I will get the affected motion that I expect. I hit the up button and I toggle it on and then toggle it off. Notice that the color tuple, which is the last line in idle that got printed, is not black. It's the 130, 110, 20. And that fourth value is for alpha value, and that's a lesson on transparency that we'll get to soon. But I can see that I am able to affect motion in 4 different ways, and the reason for that is because the color that I'm getting is different when I click on different locations, and I can see those color tuples come up differently. Now notice that when I interact with the buttons and when I'm viewing the masking surface, I can't see the thing that I'm animating because that's on the screen that the user would see. But I can notice the position here, look at the masking surface and interact with this button, toggle it on, toggle it off, and the motion still occurred on the screen. Masking is a very powerful technique because it allows us to interact with buttons that are an unusual shape. In fact, I will show that again with this up button. Now, previously, if this button was a proximity detection and it was rectangular in shape, then the proximity or the interval testing, well, there's 2 methods. The interval testing would mean that if I clicked right in the middle of the button, which is black here because of the odd shape of the button, then it would have affected upward motion. Because the interval testing is crude, it's just testing an alignment for horizontal and vertical. And the mouse position here on a button like this is right in the middle of the horizontal and vertical intervals that represent its graphic. But there's no interaction with masking. If this was proximity detection and this button had some center that I would be detecting the distance to, then clicking here again would turn the button on, because I am right in the middle. But with masking, the interaction is pixel perfect. I can get really close to the edge of any of these buttons, and it's not going to turn the button on, because I literally have to click on any pixel of the button's color in order to get the desired motion. This is pixel perfect interaction detection. However, because we're composing a different surface, we have two surfaces that we're working with, the screen that the user sees, and then a corresponding mask of all different colors of everything that could be interacted with. And creating two graphic pixel matrices, even though only one is seen by the user, is very processor intensive. So this technique is not a desirable technique if speed is important in the program that you're writing. Let's finish up with Now You. You have seen how a single color representation of a button can be drawn on a surface that the user never sees to represent a corresponding graphic that the user can see on the screen. Colors can be checked on this mask surface to detect what the mouse is clicking on. This is a CPU inefficient process, but it's capable of pixel perfect detection. Use this code file as a stub to implement a pause button that uses this technique. Have fun.